Light has a speed limit. Nothing in the universe can beat it. Not a rocket, not a signal, not gravity itself, not even the empty vacuum of space pushing on nothing. Every physicist alive will tell you this number without blinking. 299,792,458 meters per second. What almost none of them will tell you, because almost none of them actually know, is why that number and not some other number. Why not a little faster? Why not infinite? Why a limit at all? Here is what should bother you about this. A photon has no mass, 0. Not a small amount, none. In every other corner of physics, speed is a negotiation between force and resistance. Push a shopping cart, it resists you a little. Push a truck, it resists you a lot. The resistance comes from mass. Take away the mass and the resistance should vanish along with it. A massless thing, pushed by even the faintest whisper of energy, should be able to reach any speed at all, including infinite speed, instantly. And yet, light, the most massless thing we know of, refuses to go 1 inch per second faster than that one fixed number. It doesn't get there gradually either. It doesn't ease up to the limit the way a car eases toward its top speed. A photon is born at exactly that speed, and it dies at exactly that speed, and at no point in its existence is it ever anything else. That is the puzzle we are going to take apart tonight. Not what light is, we'll get to that, but why the universe drew a line in the sand at that specific number and made it impossible for anything to cross. Start with the most obvious wrong answer, because it's the one almost everyone reaches for first. Maybe light is just really, really fast, the way a cheetah is fast or a bullet is fast, an upper bound of ability rather than a law. Under this view, if we built a strong enough engine, we could eventually nudge something past it. This was actually the working assumption for most of scientific history. Nobody thought the speed of light was special. They thought it was simply the fastest velocity anyone had happened to measure. Galileo tried to measure it directly in the 1600s, using 2 men on distant hilltops with covered lanterns, uncovering them in sequence and trying to time the delay. He failed. Light was too fast for the equipment of the era. But the assumption behind the experiment was telling. He treated light's speed like a number waiting to be pinned down, the way you'd time a running horse. Just a big number, not a boundary. The first hint that something deeper was going on came from a completely different direction: electricity and magnetism. In the 1860s, a Scottish physicist named James Clerk Maxwell was studying how electric and magnetic fields relate to each other. He wasn't thinking about light at all. He derived a set of 4 equations, still taught to every physics undergraduate today, describing how a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field, each one regenerating the other as it moves outward. When Maxwell calculated how fast this self-sustaining ripple would travel through empty space, using nothing but numbers measured in electricity experiments with batteries and coils and magnets, the answer that fell out of the math was 299,792,458 meters per second, the exact speed of light, measured completely independently from a field of physics that had on the surface nothing to do with optics. This was the moment light stopped being a fast thing and became a specific physical phenomenon with a specific derivable speed. Maxwell had shown that light is an electromagnetic wave, a ripple of electric and magnetic fields chasing each other through space, and that its speed isn't arbitrary. It's baked into the basic constants of electricity and magnetism themselves. Change those constants and you change the speed of light. Leave them alone and the speed of light is locked in by the structure of the universe, not by how hard anything is being pushed. But Maxwell's discovery only relocated the mystery. It didn't solve it. If light's speed comes from the properties of electric and magnetic fields, the next obvious question is, relative to what? A wave needs something to wave in. Ocean waves need water. Sound waves need air. If light is a wave in the electromagnetic field, and that field fills space, then space itself must be filled with some kind of substance for the field to ripple through. Physicists in the late 1800s gave this hypothetical substance a name: the luminiferous ether. It had to be strange stuff, rigid enough to support waves vibrating hundreds of trillions of times a second, yet so thin and frictionless that planets could sail through it for billions of years without slowing down even slightly. Nobody liked these requirements, but nobody had a better idea either. If the ether existed, there was a way to catch it in the act. Earth orbits the Sun at about 30 kilometers per second. If space itself is filled with a stationary ether, then Earth should be plowing through it, the way a boat plows through still water. Light traveling in the same direction as Earth's motion through the ether should arrive slightly faster than light traveling against it. The same way sound from a source in front of you, moving with the wind, reaches you differently than sound from a source moving against the wind. In 1887, two American physicists, Albert Michelson and Edward Morley, built an extraordinarily precise instrument to detect this difference. They split a beam of light in two, sent the halves down perpendicular paths, bounced them off mirrors, and recombined them, looking for the tiny timing mismatch the ether should have caused. They found nothing. Not a small effect. Nothing. The speed of light was identical in every direction, regardless of Earth's motion, to the limits of what their instrument could detect. They repeated the experiment at different times of year, when Earth's orbital direction had completely reversed. Still nothing. It was one of the most famous null results in the history of science, an experiment that worked perfectly and simply refused to find what everybody expected it to find. For almost 20 years, this sat as an open wound in physics. The wave theory of light demanded a medium. The best candidate medium, when hunted for directly, wasn't there. Something had to give. In 1905, a 26-year-old patent clerk in Bern, Switzerland, working on physics in his spare time, gave. Albert Einstein didn't try to rescue the ether. He deleted it. He proposed that the speed of light is not the speed of a wave relative to some hidden medium. It is a fixed, unchanging property of the universe itself, the same for every observer, no matter how fast that observer is moving, no matter which direction they're moving in, no matter what the source of the light is doing. Not the same relative to the ether, the same, full stop, for everyone. This sounds like a small tweak. It is not. Follow the consequence honestly, and it breaks something you have believed since you were old enough to walk. In ordinary experience, velocities add. If you are on a train moving at 60 kilometers an hour, and you throw a ball forward at 20 kilometers an hour, someone standing on the platform sees the ball moving at 80. Speeds stack. That is not a law of physics you were taught in school so much as a fact you absorbed by living in the world. Einstein's postulate says light doesn't do this. If you are on a spaceship moving at half the speed of light, and you switch on a flashlight pointed forward, someone watching from a stationary platform does not see the light moving at 1.5 times its normal speed. They see it moving at exactly the normal speed. Not almost the same, exactly the same, no matter how fast the ship goes. For this to be true, for two different observers moving at wildly different speeds, to measure the exact same light beam and get the exact same number for its speed, something else has to be flexible enough to absorb the difference. Ordinary intuition assumes space and time are a fixed, universal backdrop, the same stage for everyone, and it's only things moving around on that stage whose measurements differ. Einstein's insight was that this backdrop is not fixed. Space and time themselves stretch and compress, differently for different observers, specifically in whatever way is required to keep the speed of light constant for everybody. The observer on the fast-moving ship experiences time running slower, relative to the platform observer, distances along the ship's direction of travel contract. These aren't illusions or measurement errors caused by faulty clocks. They are what actually happens to space and time when things move, and they happen in exactly the precise amount needed, so that no matter your velocity, when you measure a beam of light going by, you get the same number every time. This is the first real answer to our question, and it's not the one people expect. The speed of light isn't a speed limit because light is fast. It's a speed limit because the speed of light is the fixed point the entire structure of space and time is built around. Space and time are the flexible things. Light speed is the one number in the whole system that doesn't move. Once you accept that, a second question opens up immediately, and it's the one that actually explains why nothing can go faster. If space and time bend and stretch to protect the constancy of light speed, what happens to something with mass, trying to catch up to that speed? Follow a spaceship as it accelerates. At low speeds, everything works the way Newton described 3 centuries ago. Apply a force, get acceleration, simple as that. But as the ship's speed climbs toward a meaningful fraction of light speed, something changes. The same amount of thrust produces less and less additional speed. It isn't that the engines are failing, it's that the ship's effective resistance to acceleration, its inertia, is increasing as its speed increases. At 90% of light speed, that inertia has already grown by a factor of more than 2 compared to when the ship was sitting still. At 99%, it's grown by a factor of 7. At 99.99%, over 70. The closer you get to the speed of light, the more energy it costs to gain the same additional sliver of speed, and the returns don't merely diminish, they diminish toward infinity. To actually reach light speed, a massive object would need infinite energy. Not an enormous amount, infinite. The universe doesn't have infinite energy to give any single object, and even if it did, no amount of pushing gets you across a boundary that recedes exactly as fast as you approach it. This is why the speed of light isn't just the fastest speed anyone has happened to measure. It's a genuine wall, built into the relationship between mass, energy, and motion that no amount of engineering can push through. A rocket can get arbitrarily close. Particle accelerators today routinely push protons to 99.9999991% of light speed, but the gap between that number and 100%, however microscopically small, can never fully close for anything that carries mass. Now, flip the situation around and look at something with no mass at all, and the puzzle we opened with stops being a puzzle and starts being an inevitability. There is an equation in physics, not a famous one, not the one on the t-shirts, that ties together an object's total energy, its momentum, and its mass. The famous equation, energy equals mass times the speed of light squared, is a special, simplified case of it, one that only applies to something sitting perfectly still. The complete version includes momentum, and when you set an object's mass to exactly 0 in that complete equation, something remarkable falls out. The mass term disappears entirely, and what's left says that the object's total energy equals its momentum multiplied by the speed of light. Nothing else. No mass to hide behind, no rest state to fall back into. This means a massless object cannot have 0 momentum, because 0 momentum in that equation means 0 energy, and 0 energy means the object doesn't exist in the first place. There is no such thing as a massless object standing still. If it has any energy at all, and it must, or there's nothing there, it must be moving. And there is only one speed available to it. The one speed that is not a choice, the one number space-time itself is built around. A massive object can move at any speed below light speed and can, in principle, be brought to rest. A massless object has exactly one available speed, and it is born already moving at it from the very instant it comes into existence. This is the real shape of the answer. Massive things can never reach the speed of light because doing so would cost infinite energy. Massless things can never be anything other than at the speed of light, because having any energy at all, with 0 mass, mathematically requires it. The two halves of the puzzle turn out to be the same fact, viewed from opposite sides. Light isn't obeying a speed limit imposed from outside. Light's existence and its speed are the same statement. It's worth pausing here on something people frequently get wrong when they try to picture this from light's own point of view. You'll sometimes hear that a photon experiences no time, that from light's perspective, its birth and its absorption happen simultaneously, that the entire universe is compressed to a single point in its direction of travel. These claims get repeated constantly, and they are, strictly speaking, meaningless. Special relativity lets you describe the universe from the point of view of any observer moving slower than light. You can construct a valid reference frame for a person, a spaceship, an electron. You cannot construct a valid reference frame for something moving exactly at light speed. the mathematics that lets you translate from one observer's measurements to another's simply breaks down at that speed. You end up dividing by zero. This isn't a technical inconvenience to be waved away. It's telling you that the question, what does the universe look like from a photon's perspective, isn't a hard question with a strange answer. It's not a valid question at all, the same way what is north of the North Pole isn't a hard question about geography. A photon doesn't have a wristwatch ticking impossibly slowly. It doesn't have a wristwatch. If the speed of light really is this fundamental, not a fast speed, but the fixed point the geometry of space and time is anchored to, you'd expect it to show up everywhere gravity and geometry are involved, not just in the mechanics of accelerating rockets. And it does, in a way that reframes something you've probably heard stated slightly wrong your whole life, that gravity bends light. Gravity doesn't reach out and grab light the way it grabs a thrown baseball. Isaac Newton's theory of gravity works by treating mass as the source of an attractive pull proportional to how much mass is involved. Run light's zero mass through Newton's gravity equation, and the force comes out to exactly zero. According to Newton, gravity should have absolutely no effect on light. A beam passing near a star should sail on in a dead straight line, utterly indifferent to the star's presence. But that isn't what telescopes see. Starlight grazing the edge of the sun bends. Entire galaxies act as gravitational lenses, warping and magnifying the light of objects behind them. Something is clearly happening. If it isn't a force pulling on mass that isn't there, what is it? Gravity doesn't reach out and grab light the way it grabs a thrown baseball. Isaac Newton's theory of gravity works by treating mass as the source of an attractive pull, proportional to how much mass is involved. Run light's zero mass through Newton's gravity equation, and the force comes out to exactly zero. According to Newton, gravity should have absolutely no effect on light. A beam passing near a star should sail on in a dead straight line, utterly indifferent to the star's presence. But that isn't what telescopes see. Starlight grazing the edge of the sun bends. Entire galaxies act as gravitational lenses, warping and magnifying the light of objects behind them. Something is clearly happening. If it isn't a force pulling on mass that isn't there, what is it? Einstein's answer, arriving a decade after his work on the speed of light, was that gravity isn't a force at all in the way Newton imagined. Mass and energy warp the geometry of space-time itself, creating curves and valleys the way a heavy ball placed on a stretched rubber sheet creates a dip. Objects moving through that warped space-time aren't being pulled off a straight path by an external force. They are moving in the straightest possible line available to them, given that the space they're moving through is no longer flat. A planet orbiting a star, a comet swinging past, and a photon skimming by are all doing the same thing, following the most direct route through a space that has been reshaped by mass. Light bends near the sun, not because gravity is tugging on something with no mass to tug, but because the space the light is moving through has been curved, and light, like everything else, has no choice but to follow the shape of the space it's in. This has a strange and testable consequence for a photon's energy. A photon climbing out of a gravity well, moving away from a massive object, working, in a loose sense, against the curvature, cannot slow down. It has exactly one allowed speed and no mechanism for shedding it, so instead it pays its toll a different way. It loses frequency. A photon leaving the surface of a star arrives further out with a slightly longer wavelength than it left with, bluer light stretched toward red. This is called gravitational redshift, and it has been measured directly, first with light from dense stars, later with atomic clocks placed at different heights in Earth's own gravitational field, clocks that run at measurably different rates depending on how deep in Earth's gravity well they sit. The effect is small on Earth, but it is not zero, and modern GPS satellites have to correct for it constantly, or your phone's location would drift by kilometers within a single day. This isn't an exotic prediction confirmed once in a physics lab decades ago. It's a correction running quietly in the navigation system in your pocket right now, because the speed of light being fixed forces energy, rather than speed, to be the thing that bends under gravity's influence. Push this relationship to its extreme, and you get the sharpest illustration there is of why light's speed limit is absolute rather than merely very high. Around an extremely massive, extremely compact object, a black hole, space-time curves so severely that at a certain distance from its center, called the event horizon, the geometry tips over entirely. Beyond that boundary, every possible path forward, in every direction you could point, leads only further in. This is often described as gravity becoming too strong to escape, as though it's a tug of war that light is simply losing. That framing undersells what's actually happening. It isn't that light is trying to escape and failing because the pull is too strong. It's that past the event horizon, there is no direction that counts as out anymore. Space itself has been folded in such a way that outward has stopped being an available option for light or for anything else. Nothing needs to be caught by black holes. There's simply nowhere else to go. And there is a region just outside that boundary called the photon sphere, where the curvature is strong enough to bend light into a complete circle without quite crushing it. Light entering this region at exactly the right angle can orbit a black hole indefinitely, chasing its own tail forever, trapped not by force, but by geometry. If you could somehow stand in that region and shine a flashlight sideways, the beam would eventually curve all the way around and strike the back of your own head. This isn't speculative. The Event Horizon Telescope's famous images of the shadow cast by a black hole are pictures of exactly this effect. Light bent by geometry into an orbiting ring around the darkness at the center. All of this, the failure to detect an ether, the equations that punish acceleration toward light speed with runaway energy costs, the bending of starlight, the reddened photons climbing out of gravity wells, the light trapped in permanent orbit around a black hole, is the same fact expressed in different settings. The speed of light isn't the ceiling on how fast things can go. It's the fixed rate that space and time themselves are built to protect. The one number in the whole system nothing is allowed to renegotiate. Mass buys you the privilege of moving slower than that number and eventually stopping. Zero mass costs you that privilege entirely and leaves you with exactly one speed forever, from the instant you exist to the instant you don't. There's a final piece to this puzzle, one that seems at first glance to break everything we've just built. In the early 20th century, physicists discovered that pairs of particles, often photons, can be produced in a way that links them together no matter how far apart they later travel. Measure a property of one, and the other instantly reflects a corresponding result, even if it's on the opposite side of the galaxy. Einstein hated this. He called it spooky action at a distance, and for good reason. If information were genuinely leaping between two particles instantaneously, faster than any signal, it would appear to violate the very speed limit we've spent this entire journey establishing. Decades of increasingly precise experiments, testing what's known as Bell's inequality, most decisively in the work that earned the 2022 Nobel Prize in Physics, have confirmed that this correlation is real. The particles genuinely are not carrying preset hidden instructions the way a pair of gloves sent to opposite ends of the world would be. Something about their connection really does resolve instantly, regardless of distance. And yet, crucially, no usable message travels faster than light when this happens. The individual result each observer sees is completely random. Only when the two experimenters later meet or send each other an ordinary light-speed limited message comparing notes does the underlying correlation become visible. You cannot use entanglement to send a signal to a friend across the galaxy any faster than a radio wave could carry the same news. Nature protects its own speed limit by hiding the connection inside randomness. You can share a secret, but you cannot send a message. So the light-speed boundary survives its strangest challenge intact. Entanglement reveals that two particles can be linked in a way that has nothing to do with the distance between them, that, at some level, the space separating them may be less fundamental than it appears, but it does not let anything outrun light. If anything, it deepens the picture we've been building all along. Distance and time are not the fixed, universal backdrop they feel like from inside a human life. They are flexible. The one thing in this entire universe that isn't flexible, that every experiment for over a century has failed to bend even slightly, is that single number Maxwell first calculated from equations about batteries and magnets. A number built so deeply into the structure of reality that space and time themselves rearrange around it rather than let it move even a fraction of a percent. That's the actual answer to why nothing can go faster than light. It was never a rule imposed on the universe from outside, like a speed sign posted on a highway. It's closer to the truth to say the universe doesn't have a highway at all in the way you're picturing one. It has a fixed rate at which cause can turn into effect, and everything else, the flow of time for a moving observer, the length of a speeding ship, the bending of a star's light, the frequency a photon carries as it climbs away from a black hole, is what has to give, has to flex, has to rearrange itself, so that one number can stay exactly, permanently, unmovably the same. We've spent this first stretch establishing why light moves at the one speed it moves at, and why nothing else can catch it. But we've been dancing around a much stranger question this whole time, and it's time to face it directly. What, exactly, is the thing that's moving? We've talked about light bending, light stretching, light orbiting black holes, treating it, this whole time, almost like a well-behaved traveler obeying traffic laws. But light does not behave like a traveler. It behaves like nothing else human beings have ever encountered, and the story of how we figured that out is, if anything, stranger than the story of its speed. Rewind to the final years of the 1800s. Physics, at that point, believed it had more or less finished the job. Maxwell's equations described light as a wave in the electromagnetic field. Newton's mechanics described the motion of everything with mass. Thermodynamics described heat and energy. A famous, possibly apocryphal, remark attributed to the physicist Lord Kelvin around this time held that physics was essentially complete, with only a couple of minor details left to iron out. One of those minor details was a stubborn little problem involving hot objects and the color of the light they give off. Every object with a temperature radiates energy. Heat a piece of metal and it eventually glows. First a dull red, then orange, then a blinding white if you get it hot enough. Physicists wanted a formula that could predict, for an object at any given temperature, exactly how much of each color it should radiate. Using the wave theory of light and the laws of thermodynamics, the calculation seemed straightforward enough to set up. But when physicists actually worked through the math, the answer that came out was absurd. The equations predicted that a hot object should radiate more and more energy as you move toward higher and higher frequencies, blue, then violet, then ultraviolet and beyond, with no upper limit at all. Taken at face value, this meant that any object with any temperature above absolute zero, including your own body, including the pages of a book sitting quietly in a library, should be blasting out infinite energy in the form of ultraviolet and X-ray radiation. Obviously, nothing like this happens. You are not currently being incinerated by your own toaster. Physicists called this failure the ultraviolet catastrophe, and it wasn't a minor detail at all. It meant that something in the foundation of how physics understood energy and light was fundamentally broken. In 1900, a German physicist named Max Planck found a way to make the math match reality, and he did it by breaking a rule nobody had ever thought to question. Planck proposed, purely as a mathematical trick to force the equations to behave, that energy at a given frequency isn't emitted or absorbed in a smooth, continuous stream. It comes in fixed, discrete chunks, a minimum unit that can't be subdivided. The size of that chunk depends on frequency. High-frequency light comes in expensive chunks. Low-frequency light comes in cheap ones. Once Planck plugged this assumption in, the ultraviolet catastrophe disappeared. The formula matched the data from real, glowing objects almost perfectly. There was just one problem. Planck himself didn't believe his own assumption was physically real. He treated it as bookkeeping, a mathematical convenience that happened to produce the right numbers, and he spent years afterward trying to find a way to derive the same result without it. He never succeeded, because there was no such way to find. The chunks were real. It took 5 years and a different physicist to say so out loud. In 1905, the same year he was quietly overturning the assumptions behind space and time, Albert Einstein took Planck's mathematical trick and asked what would happen if it wasn't a trick at all. If light itself, not just the process of absorption and emission, genuinely traveled in discrete packets. He applied this idea to a puzzling experimental result called the photoelectric effect. Shine light on certain metals and electrons come flying off the surface. This much had been known for years, and on the surface it seemed like something the wave theory of light should explain easily enough. A wave carries energy, dump enough energy into a metal, and electrons eventually get shaken loose. But the details refuse to cooperate with that picture. According to wave theory, a brighter light, a bigger wave, should deliver more energy and should therefore be more effective at knocking electrons free, regardless of color. Instead, experiments showed that color, meaning frequency, was the only thing that mattered. Shine as much dim red light on a metal as you like, for as long as you like, and if the frequency is below a certain threshold, not a single electron will ever be ejected. The light could shine for 1,000 years and nothing would happen. Switch to a faint beam of violet or ultraviolet light, well above that threshold, and electrons pop off the surface immediately, with no delay at all, even though far less total energy is being delivered. Einstein's explanation was that light doesn't arrive as a smooth wave gradually depositing energy. It arrives as individual, indivisible packets, each one carrying a fixed amount of energy determined entirely by its frequency. Higher frequency, more energy per packet. Lower frequency, less. A packet of red light, no matter how many of them you throw, might simply not carry enough energy in each individual hit to free an electron. The same way throwing 1,000 ping-pong balls at a brick wall won't break it, no matter how many you throw, while a single well-aimed rock will. A packet of violet light carries enough energy in one single hit to do the job instantly. Brighter light means more packets arriving per second, more electrons ejected overall. But it does nothing to change the energy each individual electron receives. Only frequency controls that. This explained every strange detail of the photoelectric effect in one clean stroke, and it is the specific piece of work, not relativity, despite what most people assume, for which Einstein was awarded the Nobel Prize in 1921. These packets didn't have a name yet. For over 2 decades, physicists referred to them awkwardly as light quanta. It wasn't until 1926 that an American chemist named Gilbert Lewis coined the word that stuck: photon. And here is where the story takes its strangest turn, the one that trips up almost everyone encountering it for the first time, including plenty of people who've read a popular science book or two. The instinct, on hearing that light comes in discrete packets, is to picture Newton's old idea reborn. Tiny solid bullets of light, particles in the ordinary sense, little glowing marbles streaming through space. This instinct is wrong, and it's wrong in a way that matters. Go back 100 years earlier than Einstein, to 1801, and an experiment performed by an English polymath named Thomas Young that had already demolished the particle theory of light once, decisively, on its own terms. Young took a beam of light and passed it through a barrier with 2 narrow, closely spaced slits cut into it, then let the light fall on a screen behind. If light were a stream of particles traveling in straight lines, Newton's corpuscles, you would expect exactly 2 bright strips on the screen, one behind each slit, the way 2 streams of thrown sand would produce 2 piles. That is not what Young saw. Instead, the screen showed a whole series of alternating bright and dark bands, spreading out well beyond where the 2 slits were, fading gradually toward the edges. This is called an interference pattern, and it is the unmistakable signature of a wave. Drop 2 stones into a still pond at the same moment and watch the ripples spread from each one and overlap. In some places, the ripples add together and the water rises higher. In other places, a peak from one ripple meets a trough from the other, and they cancel out completely, leaving flat water even though two separate disturbances are passing through that exact spot. Young's light was doing precisely this. In some places on the screen, light plus light was producing more light exactly as you'd expect. But in other places, light plus light was producing darkness, total, complete darkness, in a region that would have been lit if either slit alone were open. Particles moving in straight lines cannot cancel each other out into nothing. Waves do this routinely. Young's experiment looked, for over a century, like the final word. Light is a wave, not a particle. So how can both of these things be true at once? How can light be quantized into discrete, indivisible packets, each with a fixed energy determined by frequency, the particle-like behavior Einstein needed to explain the photoelectric effect, while also spreading out, interfering with itself, and canceling into darkness the way only a wave can? The most direct answer came from an experiment performed in 1923 by an American physicist named Arthur Compton, and it's worth walking through carefully because it's the single cleanest piece of evidence that light genuinely behaves like a particle under the right conditions, not just metaphorically. Compton fired X-rays, high-frequency light, at electrons and looked closely at what happened after the collision. If light were purely a wave, the scattering should follow one predictable pattern with no change in frequency regardless of angle. Instead, Compton found that the X-rays that scattered off at an angle came out with a measurably longer wavelength, lower frequency, lower energy than the X-rays that went straight through. Meanwhile, the electrons themselves recoiled physically, exactly as though something with real, measurable momentum had struck them and bounced off, transferring part of its momentum and energy in the collision, the same way one billiard ball transfers momentum to another on contact. When Compton worked out the angles and energies using the mathematics of a particle-on-particle collision, treating the X-ray as carrying momentum equal to its energy divided by the speed of light, the numbers matched his measurements exactly. This wasn't a wave gently depositing energy into a spread-out region of space. This was a discrete, localized bundle physically colliding with a discrete, localized electron, the way one object collides with another. Compton won the Nobel Prize for this in 1927, and the effect that bears his name has been repeated and confirmed in laboratories thousands of times since. So, which is it? Young's slits say wave. Compton's collisions say particle. The honest answer, and the one that took quantum field theory decades to fully articulate, is that the question itself is built on a false assumption, the assumption that wave and particle are two separate boxes, and reality has to pick one. They aren't separate boxes. Picture, instead of a marble and a ripple, as two competing images, something closer to a plucked guitar string. The string has a wave nature. It has a wavelength, a frequency. It vibrates in a spread-out pattern along its whole length. But you cannot pluck it with half the minimum amount of energy required to sound a note. There is a smallest possible disturbance the string will support, a smallest quantum of vibration, and every actual pluck delivers energy in whole multiples of that amount. The string is not switching back and forth between being a wave thing and a particle thing, depending on how you look at it. It is one thing, a vibrating field with quantized energy levels, and depending on what you choose to measure, the shape of the vibration across its length, or the discrete energy delivered when it's struck. You see different faces of that one underlying reality. Light works the same way, except the vibrating medium isn't a physical string. It's the electromagnetic field itself. The same field Maxwell described, filling every point of empty space, existing everywhere at every moment, whether or not anything is currently disturbing it. When you disturb that field, an electron accelerates, an atom releases energy, a nuclear reaction fires. A ripple spreads outward through it, exactly the way a plucked string vibrates along its length. And that ripple has all the properties of a wavelength, a frequency, the ability to interfere constructively or destructively with other ripples in the same field, exactly as Young's experiment demonstrated with such clarity. But the field, like the guitar string, does not allow disturbances of arbitrary, continuously variable size. Its energy is quantized. You cannot excite it with half a unit of energy at a given frequency, only with whole number multiples of a fixed minimum amount. And that minimum, indivisible unit of excitation is what we call a photon. It is not a marble hiding inside a wave, alternating identities depending on the experiment. It is one physical entity, a discrete quantum of vibration in a universal field, and Young's interference pattern and Compton's billiard ball collision are two different measurements of the exact same thing. The way measuring a guitar string's pitch and measuring the force of its pluck are two different measurements of the exact same vibrating string. This reframing matters because it answers a question that trips up even careful thinkers. What is a photon made of? People instinctively want an answer built from smaller ingredients, the way a proton is made of quarks, or a water molecule is made of hydrogen and oxygen. Fire high energy particles at a proton and you can watch it come apart into its constituent quarks, and the gluons binding them together. This has been done repeatedly in colliders around the world, and it's how we know quarks are real. Do the same thing to a photon at any energy physicists have ever managed to reach, and nothing comes apart. There are no smaller pieces inside a photon waiting to be found. As far as every experiment ever performed can tell us, the photon is elementary, a fundamental excitation of a fundamental field with nothing beneath it. Asking what it's made of, in the sense of asking for smaller ingredients, is a question built on a false premise, the same way asking what a musical note is made of, in terms of smaller sub-notes, misunderstands what a note actually is. A note is a pattern of vibration, not an assembly of parts. A photon is a quantum of vibration in a field that fills the universe, and there is nothing underneath that description for the question to land on. There is one more property worth understanding here, because it explains something people notice constantly without knowing why. Polarized sunglasses, 3D movie glasses, the way certain camera filters cut glare off water. The electromagnetic field, when it ripples, doesn't just have a frequency. It has a direction the electric part of the disturbance is oscillating in, perpendicular to the direction the wave is traveling. This is called polarization. And it's a completely real, measurable property, not a hidden internal part, but a description of the shape the field's oscillation is tracing out as it moves. Light reflecting off a flat horizontal surface, like water or a car hood, tends to become polarized in one particular direction during the reflection. And polarized sunglasses are built with a filter that blocks exactly that direction, cutting the glare, while letting other light through relatively unaffected. Nothing about a photon's internal machinery is doing this. The polarization is a property of the field's motion itself, the same way the direction a rope is being whipped up and down versus side to side is a property of the rope's motion, not a hidden gear inside the rope. Where do these excitations actually come from in the everyday sense? What physical event has to happen for a photon to be born in the first place? The answer traces back to the architecture of the atom, and it required physicists to abandon another comfortable, intuitive picture, the idea of electrons as tiny planets orbiting a nucleus like a miniature solar system. That picture, appealing as it is, cannot survive contact with the laws of electromagnetism themselves. Maxwell's own equations say that an accelerating electric charge radiates energy, and a charge moving in a circle is constantly accelerating, changing direction moment to moment, even if its speed never changes. An electron genuinely orbiting a nucleus the way a planet orbits a star should therefore be radiating energy continuously, losing altitude with every loop, and should spiral into the nucleus and collapse the atom in a fraction of a second. Every atom in the universe on this picture should have self-destructed almost instantly after forming. Atoms obviously do not do this. Something about the solar system picture had to be wrong. The resolution, developed through the 1910s and 1920s, is that electrons in an atom don't occupy arbitrary orbits at arbitrary distances the way planets can occupy any orbital radius depending on how they formed. They occupy specific discrete energy levels, rungs on a ladder, not points on a continuous ramp. An electron can sit on one rung or another rung, but never in between. This isn't a rule imposed from outside. It falls directly out of treating the electron not as a tiny orbiting ball, but as a wave-like pattern of probability wrapped around the nucleus. A pattern that only fits neatly into certain specific shapes. The same way a guitar string clamped at both ends can only vibrate at its fundamental pitch or whole number multiples of it, never at some arbitrary fraction in between. When an electron sitting on a higher rung drops to a lower one, the atom loses a very specific exact quantity of energy, the difference between those two rungs, no more and no less. And that energy has to go somewhere, because energy cannot simply vanish. It gets released as a single photon, and because the photon's energy is fixed entirely by its frequency, the frequency of that photon is locked to the size of the drop with mathematical precision. A large drop produces a high-frequency, high-energy photon. A small drop produces a low-frequency, low-energy one. This is why heated gases don't glow with a smooth, even spread of every possible color. They glow at very specific discrete frequencies, producing narrow, bright lines when you pass the light through a prism, each line corresponding to one particular rung-to-rung transition available to that particular element's electrons. Hydrogen has one distinctive fingerprint of lines. Neon has a different one. The reason neon signs glow the specific shade of red-orange they do is a direct, exact readout of the energy gaps between rungs in a neon atom. Sodium street lamps glow their distinctive yellow for the same reason, tied to sodium's own electron structure. This is also the tool that lets astronomers determine what a star 90 million light-years away is made of without ever traveling there. They spread its light through a prism, read off the pattern of bright and dark lines, and match that fingerprint against the known signatures of hydrogen, helium, oxygen, and every other element whose atomic transitions have been measured in a laboratory here on Earth. Every photon carries, encoded in its exact frequency, a signed confession identifying precisely which atomic transition in which element produced it. There's a further wrinkle worth understanding because it's the exact mechanism behind one of the most consequential inventions of the 20th century. An electron doesn't drop to a lower rung purely on its own schedule. Left alone, an excited electron will eventually fall, releasing its photon at some random, unpredictable moment. This is called spontaneous emission, and it's genuinely random in the deepest sense the word can mean in physics, not just unpredictable due to missing information. But there is a second way to trigger the drop. If a photon happens to pass by an electron that is already sitting in an excited state, and that passing photon carries exactly the right energy to match the gap the electron would fall through anyway, its presence can nudge the electron into falling immediately, rather than waiting. And the photon released by this triggered fall is not a random new photon. It emerges as an exact clone of the one that triggered it. Same frequency, same direction of travel, marching in perfect lockstep, phase matched precisely. This is called stimulated emission, and it is the entire operating principle behind the laser, an acronym, literally, for light amplification by stimulated emission of radiation. Build a chamber full of atoms with their electrons deliberately excited, let a single photon in, and it triggers a cascade. One photon becomes two identical copies. Those two trigger two more, and so on, producing a beam of light in which every single photon is a perfect, synchronized twin of every other. This is why laser light is so different from the light coming out of an ordinary bulb. A bulb's photons are a chaotic scatter of independent, randomly timed events across a whole spread of frequencies, while a laser's photons are a disciplined, marching column, all identical, all in step. Nowhere is the journey from creation to arrival more dramatic or more worth walking through slowly than the one made by the photons currently warming your skin whenever you stand in sunlight. Deep in the sun's core, immense pressure and temperature fuse hydrogen nuclei into helium, and this fusion process converts a tiny fraction of the mass involved directly into energy, following the exact relationship Einstein described between mass and energy. That energy is released primarily as extremely high-energy gamma-ray photons. And if that energy could travel in a straight line from the core to the surface uninterrupted, it would take those photons a little over 2 seconds to make the trip. The same distance light takes about that long to cross in open space. It does not take 2 seconds. It takes, on average, somewhere between 100,000 and 200,000 years. The reason is that the interior of the Sun is so extraordinarily dense that a photon produced in the core travels only a microscopic distance before slamming into an atom, being absorbed, and being re-emitted again in a new, essentially random direction, usually carrying slightly less energy than before. This happens again and again, trillions upon trillions of times, in a genuine random walk through the Sun's interior, sometimes drifting outward, sometimes drifting back in toward the core, making no reliable net progress for extraordinarily long stretches, purely by the blind statistics of an enormous number of random steps. Only after this staggeringly long, staggeringly indirect journey does the energy that began as a single gamma-ray photon in the core finally reach the Sun's surface, by which point it has been absorbed and re-emitted so many times and lost so much energy at each step that it emerges not as one gamma-ray, but effectively as a great many lower-energy, visible light photons radiating outward into space at the Sun's surface temperature of roughly 5,500 degrees Celsius. Those photons then cross the roughly 150 million kilometers of essentially empty vacuum between the Sun and Earth in about 8 minutes and 20 seconds. Utterly unimpeded, none of the absorb and re-emit chaos of the Sun's interior, just a clean, direct 8-minute sprint at the one fixed speed the whole universe is built around. Which means that any given photon warming your face on a sunny afternoon began its existence as a completely different, far more energetic photon somewhere between 1 and 200,000 years ago, and has spent all but the very last 8 minutes of that impossibly long journey trapped inside the Sun itself, bouncing from atom to atom before finally being set free to cross the dark in a straight, silent 8-minute line directly into your skin. That is not the end of the accounting either, because the energy doesn't stop once it reaches you, if that particular photon happens to strike a leaf rather than skin. It can be absorbed by a chlorophyll molecule and used to drive the chemical machinery of photosynthesis, converting carbon dioxide and water into sugar, with the photon itself ceasing to exist the instant its energy is transferred into that chemical bond. Eat the plant, or eat something that ate the plant, and your body eventually breaks that chemical bond back open, releasing the same energy that photon carried across 100,000 years and 150 million kilometers, now powering a muscle contraction, a heartbeat, a single firing neuron somewhere in the act of forming this very thought. There is a real, traceable, physical chain connecting a fusion reaction that happened in the Sun's core roughly 100,000 years before written language existed, through a photon's frantic random walk out to the surface, through its calm 8-minute flight across space, through a leaf, through a meal, and directly into the electrochemical signal your brain is generating right now. The same absorb and transfer principle is what happens inside your own eye every time you see anything at all. A photon enters through the lens and strikes a specialized molecule in the retina, and the energy it carries triggers a change in that molecule's shape, a genuinely microscopic mechanical event, one single molecule flexing because one single photon struck it, which in turn triggers an electrical signal in a nerve cell. That signal travels up the optic nerve into the brain, where it's assembled, alongside millions of other such signals arriving in the same instant from across the whole surface of the retina into the experience of seeing. The photon itself does not survive this process. It is gone the instant it's absorbed. What continues is the energy it was carrying, converted first into a chemical change, then into an electrical signal, then eventually into the specific pattern of neural activity your brain interprets as color, shape, and light. Every image you have ever seen, every sunset, every face, every word on every page you've ever read, began as a photon ceasing to exist inside your own eye. There's one more strange feature of this story that we touched on only briefly earlier, and it deserves a proper look, because it's the phenomenon that comes closest to making the universe feel genuinely alien rather than merely counterintuitive. Take a photon, and using a particular kind of crystal, split it into two lower energy photons that fly off in different directions, born from the exact same originating event. Because they came from a single shared origin and the total properties of the system have to balance out, This is simple conservation of momentum and angular momentum, nothing exotic yet. The two resulting photons are linked. If the first is found to be polarized in one particular direction, the second is guaranteed to come out polarized in a specific corresponding direction every single time. Send one of these photons to a laboratory on one side of a city and the other to a laboratory on the opposite side, and here is the part that unsettled Einstein enough that he spent years arguing against it. Until the moment a measurement is actually performed, quantum mechanics says neither photon has a definite polarization at all. Each exists in a genuine, mathematically real state of being simultaneously every possible outcome at once, not merely an outcome we simply haven't found out yet. The instant an experimenter measures the first photon and gets some specific result, the second photon, no matter how far away, no matter whether a light signal would take a full second or a full year to physically travel between them, immediately corresponds to that result, exactly as the shared origin predicted, with no measurable delay whatsoever. Einstein's objection was reasonable on its face. If this correlation is truly instantaneous, doesn't it require some kind of communication that outraces light itself? The very speed limit we spent this whole first hour proving to be inviolable. His proposed way out was that the two photons must simply be carrying pre-programmed, hidden instructions from the moment of their creation, the way sending a left glove to one city and a right glove to another produces a correlation that looks spooky but is really just information that was baked in from the start. For decades, this remained an open philosophical argument rather than a settled scientific question because nobody could see how to actually test it. In 1964, a physicist named John Bell finally found a way, deriving a precise mathematical inequality that any theory based on pre-programmed hidden instructions would have to obey, and that genuine, unresolved quantum uncertainty would have to violate. It took until the 1970s and 80s for experiments precise enough to actually run the test. And it took until 2022 for the Nobel Prize to be awarded, jointly, to the physicists whose accumulated body of work over those decades had finally closed every conceivable loophole. The verdict, confirmed again and again with steadily improving precision, Einstein's hidden gloves do not exist. The photons genuinely are undecided until measured, and the correlation between them genuinely is established faster than any signal traveling at light speed could account for. And yet, exactly as we found with the equations governing acceleration toward light speed, the boundary survives intact once you look closely enough. Neither experimenter can use this effect to send an actual message. The result each of them individually gets when they measure their photon is completely random, heads or tails, up or down, with no way to force a particular outcome. It's only when the two experimenters later compare their separately recorded lists of random results, using an ordinary method of communication that is itself bound by the speed of light, a phone call, or a radio signal, or an email, that the underlying correlation between the two lists becomes visible at all. You can build a shared secret this way. You cannot build a faster-than-light telegraph. The universe, it turns out, is willing to let two particles share a connection that has nothing to do with the distance between them, but it is not willing, under any circumstance anyone has ever managed to devise or test, to let that connection carry an actual signal past the one fixed speed everything else in this story has been organized around. Step back now and look at the full shape of what we've actually covered. We began with a single, apparently simple fact. Light moves at one fixed speed and nothing can catch it, and pulled on that thread until it led through the failure to detect a hidden cosmic medium, through the discovery that space and time themselves are the flexible things rather than the fixed backdrop they feel like, through the realization that gravity doesn't pull on light so much as reshape the space. Light has no choice but to follow, through a black hole's photon sphere where light can be made to orbit its own point of no return, through the accidental discovery that energy itself comes in indivisible packets, through the specific atomic mechanics of how those packets are born and how they die, through a 100,000-year journey out of the sun's own interior, and finally through a connection between particles that seems to ignore distance altogether, while still, somehow, refusing to break the speed limit that governs everything else. None of these are separate mysteries that happen to share a subject. They are the same underlying structure, examined from different angles, a universe built at its deepest level around one fixed, unbending number, with everything else in existence, space, time, mass, gravity, even the strange non-local links between distant particles, arranging itself around that number rather than the other way around. The next time you're outside and the sun is on your face, you now know something almost nobody standing next to you knows. That warmth is the tail end of a journey that began inside a star roughly 100,000 years ago, spent nearly all of that time trapped in a chaotic random walk through solid plasma, and then crossed the empty dark between the sun and the earth in a single clean sprint at the one speed the entire universe was built to protect. It arrived carrying, encoded in its exact frequency, a signed record of precisely which reaction, deep in a star, gave rise to it. And in the fraction of a second it takes your skin to absorb it, that 100,000-year-old packet of light will cease to exist entirely, converting the very last of its ancient energy into something as small and as strange and as real as a single degree of warmth on your skin. There is still a piece missing from this picture, and it's the piece that explains why any of this matters beyond the photon itself. We've talked about light as though its only job is to travel and eventually strike something, a retina, a leaf, a detector. But the electromagnetic field the photon belongs to is not a passive stage that light happens to perform on. It is the thing holding the physical world together, moment to moment, at every scale from a single atom to your own body sitting wherever you are right now. And the mechanism behind that is one of the strangest ideas in this entire story. Forces themselves, the pushes and pulls between charged particles, are carried out by an endless, invisible traffic of photons that never reach your eye at all. Picture two electrons drifting toward each other. In the old, pre-quantum picture, you'd say they simply repel. An invisible force reaches across the gap between them and pushes them apart, the way Newton described gravity reaching across the gap between the Earth and the Moon. Quantum field theory replaces that vague action at a distance picture with something far more mechanical. One electron emits a photon. The other electron absorbs it. The recoil from throwing that photon pushes the first electron backward. The impact of catching it pushes the second electron backward too. Do this rapidly, continuously, in both directions at once. And from a distance it looks exactly like two electrons quietly repelling each other through empty space. Up close, at the level the theory actually describes, it is a constant, furious exchange of photons back and forth, functioning as tiny messengers carrying the force between them. These exchanged photons are not the same kind you see with your eyes. Physicists call them virtual photons, and the distinction matters. A real photon, the kind streaming from a light bulb or a star, is born, travels freely through space, and eventually strikes something far away, carrying energy the whole distance. A virtual photon exists only for the brief, fleeting duration of a single interaction between two charged particles. It isn't detected. It doesn't travel anywhere in the ordinary sense. It exists as an intermediate step in a calculation, and in the physical process the calculation describes, then it's gone the instant the interaction is complete. Every magnet sticking to a refrigerator, every static shock from a doorknob, every electron staying bound in its orbit around a nucleus rather than drifting off into space. Every one of these is being maintained continuously by a traffic of virtual photons flickering back and forth between charged particles too fast and too fleeting for any instrument to directly witness one in transit. This gives the photon a strange double identity. It is simultaneously the particle of visible light, the thing crossing 150 million kilometers of space from the sun to your eye, and the fundamental unit of currency the electromagnetic force uses to transact business between any two charged particles anywhere in the universe, whether or not any light is involved at all. Every chemical bond holding a molecule together is, at bottom, this exchange happening between the electrons of neighboring atoms. The reason you don't fall through the floor you're standing on isn't that the atoms in your shoes and the atoms in the floor are somehow touching in a solid, continuous way. At the atomic scale, matter is almost entirely empty space. What actually stops you is the electromagnetic repulsion between the electron clouds of your shoes and the electron clouds of the floor, a repulsion carried out at the deepest level available to physics by exactly the same kind of photon exchange responsible for two electrons pushing each other apart across a laboratory. The floor feels solid because of light you will never see. This framework, called quantum electrodynamics, or QED, developed in the years following the Second World War by Richard Feynman and a small handful of other physicists, is not a loose or speculative sketch. It is, by a wide margin, the most precisely tested theory in the entire history of science. One of its predictions concerns a property of the electron called its magnetic moment, essentially how strongly the electron behaves like a tiny magnet. QED predicts the value of this property to more than 10 decimal places, using nothing but the theory's own internal mathematics, folding in the effects of countless virtual photons being exchanged, absorbed, and re-emitted in ever more complicated patterns. When this prediction is checked against direct laboratory measurement, the two numbers agree to better than 1 part in a trillion. To put that level of precision into a human scale comparison, it is roughly equivalent to predicting the distance between New York and Los Angeles accurately enough to be correct within the width of a single human hair. No other theory in any branch of science has ever matched experiment with anything close to that precision, and every bit of that precision is riding on the accuracy of the claim that light and matter interact through a constant, invisible exchange of photons too brief and too small for any instrument to ever directly witness one crossing the gap. There's a natural question sitting underneath all of this, one we touched on earlier from the angle of energy and momentum, but haven't yet approached from the angle of why the universe insists on it. We established that a massless particle has no choice but to move at exactly light speed. But why is the photon massless in the first place? Why does this particular particle, out of everything in nature, get to skip the one property almost every other fundamental particle carries? The answer lives inside a piece of mathematics called gauge symmetry, and while the full machinery of it belongs in a physics classroom rather than here, the core idea is reachable without the equations. Most particles in the universe, electrons, quarks, the particles that make up the nuclei of every atom in your body, acquire their mass through an interaction with a separate field that also fills all of space, called the Higgs field, discovered experimentally in 2012 after decades of theoretical prediction. Particles that interact strongly with the Higgs field behave as though they're wading through molasses, resisting acceleration, and we experience that resistance as mass. Particles that interact weakly with it barely feel the drag at all, and have correspondingly tiny masses. The photon, uniquely among the particles that carry forces, does not interact with the Higgs field whatsoever. It passes through completely untouched, unaffected, exactly as unaffected as a beam of light passing through a pane of perfectly clear glass. This isn't an accident or an oversight in the structure of the universe. It's a direct, mathematically required consequence of the specific kind of symmetry the electromagnetic field possesses, a symmetry that would be broken, and the entire theory of electromagnetism would stop making consistent predictions if the photon were allowed to have even the tiniest sliver of mass. Every experiment ever run to check has come back consistent with a photon mass of exactly 0, with the tightest measurements placing an upper limit so small it may as well be nothing at all. The photon isn't massless by luck. It's massless because the deep structural symmetry of the electromagnetic field itself requires it to be, on pain of the whole theory falling apart if it weren't. This connects to something even stranger sitting underneath the whole conversation, something we've been assuming without ever quite stating outright, that empty space isn't actually empty. Picture the emptiest possible box you could construct. Every atom pumped out, every scrap of light shielded from getting in, cooled as close to absolute zero as physics allows. Classical intuition says that box now contains nothing at all, a true silent void. Quantum mechanics says otherwise, and it says so because of a principle discovered by Werner Heisenberg in the 1920s. You cannot simultaneously know both the exact energy of a system and the exact instant that energy is measured, with unlimited precision in both at once. Applied to the electromagnetic field sitting inside that supposedly empty box, this means the field's energy can never actually settle down to a perfectly calm, perfectly zero, perfectly silent value, even in principle. It has to jitter, constantly, everywhere, at every point in space. Pairs of particles, most often an electron, and its antimatter counterpart, a positron, flicker briefly into existence, borrowing energy from the deep uncertainty built into the vacuum itself, existing for an unimaginably brief fraction of a second, and then annihilating each other again, paying that borrowed energy straight back before the universe can register the debt. This churning, ceaseless activity, occurring in every cubic centimeter of what looks and feels like total emptiness, is called the quantum vacuum. And unlike almost everything else we've discussed tonight, it isn't merely a mathematical convenience invented to make equations behave. It has been measured directly in a real laboratory pushing on real physical metal. In 1948, a Dutch physicist named Hendrik Casimir proposed an experiment to catch this invisible churning in the act. Take two uncharged, perfectly ordinary metal plates and place them extraordinarily close together in a vacuum, mere micrometers apart, with nothing touching them and no charge on either one. Classical physics offers no reason whatsoever for these plates to move. No charge means no electrical attraction, and they're far too light and too close together for gravity to matter. But because the plates are so close together, only certain sizes of quantum fluctuation can fit comfortably in the narrow gap between them, the same way only certain wavelengths of a vibrating guitar string fit between two fixed clamps. Outside the plates, in the open space surrounding them, fluctuations of every possible size are permitted, with nothing to restrict them. This creates an imbalance, more of the vacuum's restless quantum activity pressing in from the outside than is able to exist in the restricted space between the plates, and that imbalance shows up as a real, measurable force, gently but unmistakably pushing the two plates together, with no external cause of any kind. This effect, predicted purely from theory decades before anyone could measure it, has since been confirmed in the laboratory with remarkable precision. Empty space, it turns out, has a physical texture, and you can feel it if you get two pieces of metal close enough together. If the vacuum is genuinely this active, genuinely full of energy, fluctuating in and out of existence everywhere all the time, a natural next question is whether that churning could ever be coaxed into producing something real and lasting, rather than flickering back out of existence within an instant. The answer is yes, and the mechanism, called the dynamical Casimir effect, is one of the more startling confirmed results in modern physics. If you could take a mirror and accelerate it to a meaningful fraction of the speed of light, moving it fast enough, sharply enough, the rapidly shifting boundary would interact with the vacuum's constant flicker of briefly existing particle pairs in a way that can rip some of them apart before they have the chance to annihilate each other and vanish as they normally would. What would have been a fleeting, undetectable fluctuation instead becomes real, permanent radiation, light generated from nothing but the sheer motion of an empty mirror through empty space, with no bulb, no filament, no conventional source of any kind, physically accelerating a mirror that fast is far beyond current engineering. But in 2011, a team of researchers at Chalmers University of Technology in Sweden built a superconducting circuit that could simulate a mirror moving at roughly a quarter the speed of light and detected exactly this: photons emerging from what should have been silent, empty vacuum, produced by nothing but motion against the restless, ceaselessly fluctuating quantum field that fills all of space. This is worth sitting with for a moment, because it reframes something we treated much earlier in this story as a simple, settled fact. We said the electromagnetic field is a real physical entity that fills the universe. The medium of photon is a ripple in. What the Casimir effect and its dynamical cousin actually demonstrate is that this field is never fully at rest, not even in the emptiest possible corner of space, not even with every source of light and heat and matter completely removed. There is no true silence anywhere in the universe. There is only a background hum of quantum uncertainty, everywhere, always, occasionally amplified by exactly the right circumstances into something a detector or a pair of metal plates or an accelerating mirror can actually catch. There's one final thread to pull before we can pull the whole story together, and it's the one that ties the photon most directly back to the ordinary, solid matter you're made of. Earlier, we described how a photon is created when an electron drops between energy levels inside an atom, converting the atom's own stored energy into a burst of light. There is a far more dramatic version of energy converting into light, and it runs in both directions. Take an electron and its antimatter counterpart, a positron, identical to the electron in every way except for carrying the opposite electric charge, and bring them together. The moment they meet, they don't merge or combine the way two droplets of water might. They annihilate. Their entire mass, the whole of it, on both particles, converts directly into pure electromagnetic energy, typically emerging as a pair of high-energy gamma-ray photons flying off in opposite directions, each one carrying almost exactly 500,000 electron volts of energy, precisely the amount of energy locked into an electron's mass, following Einstein's own equation relating mass and energy, run here in the direction most people never think to run it, not energy becoming mass, but mass vanishing entirely and becoming energy, converted completely into two photons. Two particles that had real, measurable, weighable mass one instant earlier simply cease to exist as matter, and what remains is nothing but light, carrying away every last scrap of the energy that mass once represented, with the bookkeeping balancing out exactly, down to the smallest possible unit. This process runs the other direction too, and just as cleanly. Take two sufficiently high-energy gamma-ray photons and collide them head-on, under the right conditions, and it's possible for them to vanish entirely and produce out of pure light a brand new electron and a brand new positron, solid, massive, real particles of matter, created from nothing but the collision of two massless packets of electromagnetic energy. This isn't theoretical speculation. It's a confirmed, repeatedly observed process, predicted by quantum electrodynamics and demonstrated in high-energy physics experiments. It means the boundary between light and matter, the boundary this entire story has been quietly assuming exists. Light over here, doing its strange, massless, ever-moving thing, and matter over there, sitting still, carrying weight, isn't really a boundary at all. It's a currency exchange. Mass is one form energy can take. Light is another. Under the right conditions, the universe converts freely between them in both directions, with nothing lost and nothing gained in the trade, which brings us at last back to the question we opened this journey with, and to why the answer is so much stranger than light is simply very fast. Every atom in your body is held together by an electromagnetic force carried out through a ceaseless, invisible traffic of virtual photons. The floor beneath your feet feels solid because of that same traffic. The warmth on your skin on a sunny day is the tail end of a 100,000-year journey out of the sun's own interior, delivered across 150 million kilometers of empty space in a single unbroken 8-minute sprint. At the one fixed speed, the entire structure of space and time exists to protect. The vision that let you read every word of this sentence began with individual photons ceasing to exist, one after another, inside your own eye, converting their ancient stellar energy into the electrochemical signal you now recognize as sight. And underneath all of it, at every scale, from the flicker of particles blinking in and out of existence in an empty vacuum to the fusion reaction burning at the center of every star in the sky, the universe runs on a single fixed exchange rate between mass and light and a single unbending, unmovable speed limit that nothing, not a rocket, not gravity, not even the strange, distance-defying link between two entangled particles, has ever, in over a century of increasingly precise attempts, managed to break. Light isn't fast the way a cheetah is fast or a bullet is fast. An upper bound reached through raw ability that a better cheetah or a bigger gun might someday beat. It's fast the way the number 3 is odd. Not a record waiting to be broken, but a fixed feature of what the thing actually is. Ask why light moves at exactly the speed it moves at, and the honest answer isn't really about speed at all. It's about what has to be true. Structurally, at the deepest level physics has ever been able to reach, for a universe like this one, with matter, with chemistry, with light, with eyes capable of catching that light and turning it into an experience, to be able to exist in the first place. Before we close this out, there's a question worth asking that we've circled without ever answering directly. What actually separates the light you can see from the 99% of light you never notice at all? You've been swimming in radio waves your entire life, sitting in a room right now without a single one of them registering as anything at all. Understanding why reveals just how narrow and how strange the sliver of reality your eyes were built to catch really is. Every kind of electromagnetic radiation, radio waves, microwaves, the visible light you're reading this with, ultraviolet, X-rays, gamma rays, is exactly the same underlying phenomenon. A ripple in the same universal electromagnetic field, made of the same fundamental particle, obeying the same fixed speed limit. The only thing that separates a harmless radio wave from a lethal gamma ray is frequency. How many times per second the field is oscillating at that point. And because energy is locked directly to frequency through the same relationship Planck and Einstein worked out over a century ago, frequency alone determines how much of a punch each individual photon carries. A radio wave might oscillate 100 million times a second. Its individual photons carry so little energy that no instrument can detect them one at a time, only in the overwhelming collective flood produced by a transmitting antenna, which is why your radio doesn't work if you're only catching a handful of photons. It needs a torrent of them arriving together to register anything at all. Push the frequency up into the range of visible light, and each individual photon now carries roughly 100 trillion times more energy than that radio photon did, simply by virtue of oscillating 100 trillion times faster. Push further, into ultraviolet, and the photons now carry enough energy individually, one at a time, to break chemical bonds directly, which is exactly why ultraviolet light damages skin and radio waves don't, no matter how long you sit next to either one. It isn't that ultraviolet is a fundamentally different kind of thing than radio. It's the same thing, oscillating faster. And faster oscillation means harder individual hits. Visible light, the narrow band your eyes evolved to detect, sits in an extremely specific, extremely narrow slice of this entire range, and the reason it sits exactly there is not an accident. The sun's own surface temperature determines which frequencies of light it produces in the greatest abundance, and the frequencies the sun happens to produce most abundantly are, unsurprisingly, exactly the frequencies eyes on a planet orbiting that sun evolved to be most sensitive to. Evolution didn't design an eye and then wait for the universe to cooperate. It shaped a detector around the specific flood of photons that was already raining down, freely and constantly, on every living thing on the surface of this particular planet. If Earth orbited a much cooler, redder star, life here, if it evolved at all, would almost certainly have eyes tuned to a different, redder slice of this same spectrum, and would be just as blind to the actual visible light you're using right now as you currently are to the flood of infrared, radiating quietly off your own skin at this very moment. That last detail is worth pausing on, because it means you yourself are a source in this story, not just a receiver. Every object with a temperature above absolute zero radiates electromagnetic energy, and you have a temperature. Right now, without doing anything at all, the atoms and molecules that make you up are jostling, vibrating, colliding, and every one of those tiny random motions involves a charged particle accelerating, however slightly, and every accelerating charge radiates. You are at this very moment glowing, not in visible light, but in infrared, at a frequency corresponding almost exactly to your own body temperature. This isn't a metaphor. It's precisely how thermal imaging cameras work, and it's precisely why a person hiding in total darkness is still perfectly visible to a camera built to catch that particular slice of the spectrum. You have never, for one single second since you were born, stopped emitting light. You simply can't see the specific band you happen to be emitting it in. All of this, every frequency from the slowest radio wave to the fastest gamma ray, is the exact same physical entity we spent this entire journey taking apart, a quantum of the electromagnetic field, born the instant something disturbs that field, moving at the one fixed speed. The whole structure of space and time is arranged to protect, until the moment it strikes something and ceases to exist, converting its energy into whatever form the thing it struck can use. So here is the full shape of everything we've walked through tonight, laid out in one line, without the history and the equations wrapped around it. There is a field, filling every point of space, that has existed since the universe was young enough to still be filled with almost nothing else. That field cannot sit perfectly still, even in the darkest, coldest, emptiest patch of space imaginable. It flickers, constantly, with a restless quantum energy that occasionally becomes real enough to push on a pair of metal plates in a laboratory. When something disturbs that field with enough energy, an electron dropping between two rungs inside an atom, two particles of matter annihilating each other, a star's core fusing hydrogen into helium, the field responds with a ripple, and the smallest possible ripple it's capable of producing at any given frequency is what we call a photon, massless, structureless, carrying no internal parts to discover no matter how hard or how precisely you search. Existing only in motion because existing at rest for something with no mass would mean not existing at all. That ripple moves at exactly one speed, not because anything is pushing it there, but because that speed is the fixed anchor the whole geometry of space and time is built around, the one number so fundamental that space and time themselves bend, stretch, and rearrange in whatever way is required to keep it from ever being 0.1% different for any observer, anywhere, moving at any speed. It bends around stars not because gravity reaches out and grabs something with no mass to grab, but because the space it's moving through has itself been reshaped by mass, and the ripple, like everything else, has no option but to follow the straightest path available inside a space that is no longer flat. And when it finally strikes something, an electron in a distant detector, a chlorophyll molecule in a leaf, a single light-sensitive cell in the back of your own eye, it vanishes completely, converting every scrap of the energy it carried, sometimes across 100,000 years and 150 million kilometers, into whatever the next link in that chain needed it to become. You started this by learning that light has a speed limit, and nothing can beat it. You now know that this single fact, followed all the way down, turns out to be the same fact as why the floor holds you up, why the sun is warm, why atoms don't collapse, why black holes are dark, why two particles on opposite sides of a laboratory can seem to share a single fate, and why, whenever you open your eyes, the universe is quietly ending, one photon at a time, 100 trillion times a second, each one giving up everything it carried the instant it lands so that you can see.